Greetings, I am Behzad Razavi, and today I would like to talk about negative feedback. I'm a professor of electrical and computer engineering at UCLA, and my research interests generally lie in the area of analog and high-speed design. Today I would like to start with a basic perspective on negative feedback that leads to a simple yet useful principle. And then we will use this principle, we'll apply this principle to a number of cases. For example, how can we improve the performance of amplifiers by feedback? It also leads to the concept of virtual ground, and we'll see a number of its applications. And then we will also apply the principle to see how we can build better current sources and even suppress noise in some systems. Suppose we have bought a voltage amplifier having a gain of A0. This circuit faces at least 4 issues. Number one, the gain of the circuit depends on environmental factors such as the supply voltage and the temperature. So the gain can vary by as much as a factor of 1 to 2 in a temperature range. Number two, the gain of the circuit depends on frequency. So it is possible that beyond a certain frequency, the gain drops so much that the circuit is not very useful. So we say the bandwidth of the circuit is some value f0, and that requires that the bandwidth of the signal going through the amplifier be limited to about this range. Number three, the circuit has a finite output resistance. That means that the gain it provides is sensitive to the amount of load that it has to drive. In other words, if we have a heavy load, the voltage gain will be less than if you have a lighter load. And number four, if we look at the input-output characteristic of that amplifier, we see that for low voltage swings, the voltage gain of the circuit is A0, but as the voltage swings increase, the slope, meaning the voltage gain, drops. This is what we call nonlinearity. All these 4 issues make the use of the circuit difficult in practice. On the other hand, with negative feedback, we can improve all of these 4 difficulties. All right, so let's go ahead and take that voltage amplifier and place it in a negative feedback loop. How are y and x related? Well, we can write y over x quickly as the forward gain divided by 1 plus the forward gain. In this case, the feedback factor is 1. And we see that if the forward gain is much greater than unity, then this is approximately equal to 1. So what does that mean? It means that the output is approximately equal to the input. So in other words, the output is a good copy of the input because they're very close to each other. So we'll articulate this principle as follows. We say negative feedback creates a faithful replica of the input. We see that this copy is a close replica of the input. And we will use this principle in all of our studies today to see how negative feedback can improve systems. So let's go back to those 4 issues I mentioned and see how this principle helps us. But before we go there, I wanted to make one point. You may ask, all I have done here is to make sure that y is equal to x. So why is that better than a piece of wire? A piece of wire also guarantees that y is equal to x. So we'll come back to that in a little while. But first, we'll just stay with this simple system and see what it entails as far as the non-idealities of this amplifier are concerned. Okay, so let's start by looking at the gain variation with environmental factors, for example, with temperature. Even if the gain of A0, that original amplifier, is changing with temperature, the key is that this loop wants to make sure that the output is equal to input. So the output and input are always close to each other, so y over x is always equal to 1, even though A0 is changing significantly. So the percentage change in this gain, y over x, is much less than the percentage gain in A0 itself. All right, the second issue had to do with frequency. So again, if we apply different frequencies to the input, the output wants to create a close copy of that signal over here. So even though the gain of this amplifier is changing with frequency, like so, the overall gain from x to y remains close to 1 for a wider frequency range. In fact, all the way up to approximately a bandwidth of A0, F0. So that's another advantage of negative feedback. How about the output resistance? Well, we said that when we had A0 and its output resistance and RL, we had direct sensitivity to the load resistance for the voltage gain. But now, again, because this feedback loop wants to create a good copy of the input right here, regardless of how much load we apply to it, we conclude that the sensitivity to RL is less now. More fundamentally, what happens is that this feedback reduces the effective output resistance by a factor of 1 plus A0, so the output resistance is less than what we had before for the amplifier itself, and that's why the result is less sensitive to the load resistance. Number 4, the nonlinearity. Well, we saw that before the gain changed as the slope of this curve changed significantly, but now, again, even if the signal swing is larger, the output wants to become a close copy of the input. So the output is a relatively linear copy of the input. And that means that the gain is maintained to be 1 across a wider voltage swing range than before. And this again indicates that the system is more linear than the original A0 amplifier. All right, so these were some interesting and nice properties of negative feedback that all result from the fact that the loop wants to create a close copy of the input at over here, meaning at this input of the subtractor. All right, but remember I said how come we just don't use a piece of wire if y is equal to x? Well, here are a couple of examples to show what negative feedback can do and something that a piece of wire cannot. All right, so suppose in this negative feedback system, I take the output and divide it by some factor k, attenuate it by some factor, and then return it to the input. So then what happens? Well, we know that this negative feedback system wants to create a close replica of x over here. So whatever we have here, we also have here. So then what should we have at the input of this k block? If the output of the k block is equal to x, the input of the k block should be x divided by k. So it will be larger because k is less than 1. So we have created, again, a close replica of the input, but just taller. So we have some amplification. And this amplification can be quickly written as follows, which comes out to be 1 over k. All right, so obviously that's something that a piece of wire could not do. All right, here's another example. Suppose I have a global supply that experiences fluctuations due to various factors. And I would like to drive a certain device, which we call a load. And I would like to give a constant voltage to this load, a constant, well-defined, stable voltage. So if I just connect these two together, it won't do because the supply fluctuates with time. All right, so what should I do? Well, what if I place a source follower between the two and secure this gate at a nice, well-defined voltage? The source follower wants to have this voltage over here as well. So we would think that this voltage is now relatively independent of the supply voltage, provided that M1 is in saturation, so M1 is acting as a source follower. That's true, except that we should also keep in mind that the current driven by the load is actually not constant. Imagine you have a microprocessor here. When it's doing some computationally intensive calculations, and then it draws more current than other times. And if we draw different currents, because the output resistance of this source follower is not zero, we still get different voltages. So we have to do something about that. All right, so I'm going to play the same trick as I did there. I will take the output, this output here, divide it down by a simple resistive divider, and then bring it and subtract it from an input Vref, this input X here. So this amplifier now acts as that subtractor. And this divider acts as that K factor over there. So the same principle applies. This feedback loop wants to create a good replica of Vref over here. Vref is a constant, stable, clean voltage. So we create a good copy of that over here. And this voltage is just a number greater than 1 times Vx, because we have just divided it down. So Vout tracks Vx very well, Vx tracks Vref very well, and Vref is a constant voltage. So the voltage delivered to this load is constant, regardless of the fluctuations that we have here or the current fluctuations that we have here. So that's another beautiful property of negative feedback. And of course, this circuit is called a voltage regulator and has wide applications in all electronic systems. Now, of course, you might ask, if I already have a constant voltage, Vref, why don't I apply that directly to this load? Right? This seems obvious. I'll leave that as an exercise for you. Okay. Now, I'm going to play a trick on you and see if you can follow what I'm doing here. Remember we said that if we have an amplifier and place it in a negative feedback loop like this, the output resistance drops by a factor of 1 plus A0. All right? This is a voltage amplifier. Okay. Now suppose I redraw the circuit. Just redraw it, don't make any changes. So I draw it like this. R out is now placed over here. Node X comes to this side, and the impedance still R out over 1 plus A0. Do you agree that these two are the same circuit exactly? Okay. So now let's just change the name of this R out to RF, a feedback resistor, and let's give it an input. Like this, and then let's give it an input. So now we have an input to this network, and the input resistance is RF over 1 plus A0. Previously it was the output, now it's the input. And this circuit provides a low input resistance and is called a trans-impedance amplifier. This is of course what you would also call the Miller effect, and you can see that these are all related. These are really the two sides of the same coin. And because the impedance at this point is low, for reasonable current coming to this node, the voltage change, voltage fluctuations here are small, so we call this a virtual ground. This virtual ground has many applications in circuit design. So let's go and look at a few of them. Okay, suppose I have a common source stage, and remember that if we are trying to generate a large output swing, the circuit may become nonlinear. So how can I improve the linearity of the circuit? Well, what I remember is that if I have a trans-impedance amplifier, it provides a low input resistance. So why don't we marry these two circuits and get this? So now the drain current, the signal current coming out of M1 flows through this node and flows through this RF. So the voltage swing at this node is small. Why? Because the drain current multiplied by this resistance, which is this value, is smaller than what we had before, because we have a gain of 1 plus A0 in the denominator. The output is still large because this current flows through RF and generates a voltage swing equal to this signal current times this RF. So what we have obtained here is small voltage swings here, such that M1 remains linear, and large output swings here, so that we have some voltage gain, and we can use that for whatever we want to do. Of course, one assumption here is that A0 itself can handle this large output swing without becoming nonlinear. So A0 has to be more linear than the original common source stage that I started with. And that's possible under certain conditions. So what we see is that we have improved the linearity of circuit at this interface here. Now, where do we use that? Well, one application is actually in RF receivers. In RF receivers, we have some sort of amplifier, followed by a mixer, followed by another amplifier. And this is exactly the type of interface that we create. We have a virtual ground created by a TIA, interfacing with the output of the amplifier. So now the amplifier delivers current to this node. The voltage swing at this node and this node is small, so this interface remains linear. The amplifier and the mixer remain linear. And then we have a large output swing over here in the baseband that we can utilize. So this is widely used in almost all receivers today. All right, the concept of virtual ground has other applications as well. So here's another situation. Suppose I have a photodiode. It's just a diode that receives light and generates current. So I need to provide a voltage, so I pass this current through a resistor. That gives me a voltage. This is used in, for example, optical communications. Okay, that sounds good, but the problem is that the photodiode itself is not as clean as a current source. It has a large parasitic capacitance, CL. So the bandwidth at this node is limited to this amount. That's inevitable. So here's the trade-off I face. If I make RL large to obtain a large voltage at this point, then the bandwidth goes down and vice versa. So how do we avoid this simple trade-off? Well, let's go ahead and flip this RL around a TIA, like so. So now the RL is over here, and the current coming from the photodiode needs to go this way and then decide how to split between this capacitance and this resistance. Well, what we see is that the input impedance now is RL over 1 plus A0. So the bandwidth at this node is given by this factor times the original bandwidth that we have. Because the resistance seen has gone down by 1 plus A0, the bandwidth goes up by 1 plus A0. So the bandwidth at this interface improves by this factor. Of course, the assumption is that this amplifier has enough bandwidth, and that's a separate story. This circuit is used widely in optical communications. For example, in data centers that hold all your pictures and videos on Facebook and Google and YouTube and everyone else. All right. Virtual ground also has application in cases where we need to perform precise operations. Here's an example. Suppose I have a capacitor holding a charge of Q, and I want to deliver all of the charge of this capacitor to another capacitor. Is it possible in this form? No, because when the switch closes, the final charge that resides on C2, it depends on C1 and C2 and the initial condition on C2. So not all of Q1 ends up on C2. They just share their charge and they end up with the equal voltage between them. So that's not what we are looking for. So what can we do? Well, we're going to take this capacitor and flip it around an amplifier, just like before, to create a virtual ground. So here's the situation. C2 is around an amplifier. This is a virtual ground. So when the switch closes, all of the charge of C1 flows this way and ends up on C2. Why? Because this is a virtual ground. So after everything settles, the voltage here will be close to 0. The voltage here will be close to 0. All the charge is gone, and the only place it has to go is C2. This precise charge transfer through the virtual ground is critical in many circuits, such as integrators and amplifiers, and all of those are used in the context of analog to digital converters and filters. Okay, negative feedback can also be used to build good current sources. We know that a MOSFET operating saturation is a current source, but not a very good one, because its output resistance is limited by that of the transistor itself. So we apply a change in voltage here, this current changes quite a bit. All right, so let's take that transistor and place it in a negative feedback loop like this. I sense the source voltage of this device and bring it back and subtract it from a battery voltage by means of this amplifier. So what does this negative feedback loop do? It wants to create a good replica of this voltage over here. So if that's VB, this is approximately equal to VB. If this voltage is VB, how much is this current? It's just VB over RS. So the key point here is that this current is VB over RS regardless of what we do to this circuit. For example, let's consider the output resistance of M1 and apply voltage over here. If this voltage changes by delta V, how much current do we get through RO? This side is secured. This side is VB because this negative feedback loop wants to make it close to this voltage, right? So this voltage doesn't change. That means that the current through RO is just delta V over RO. Now we have a strange situation here. This current hasn't changed because VB doesn't want to change. This current is delta V over RO. So where does this go? Well, it has to go this way, right? There's no other way. So M1 actually creates a negative small signal current to oppose that one. So what this means is that if I try to find the output resistance of the circuit by applying a voltage to the drain of this device, changing the voltage by delta V, and looking at the change in the current is 0. So that means that the output impedance is infinity. Of course, in reality, that's not true because of the finite gain we have here, etc. But that gives you a feel for why the output impedance in this case is so much higher. Of course, you may ask, if this voltage doesn't change, how does this transistor know to generate this current? Right? Since that this voltage didn't change. I'll leave that as an exercise for you. Okay. So this circuit is called a regulated cascade or a gain boosting stage and is used in amplifiers and A to D converters and filters. All right, the last property of feedback that I wanted to share with you is reduction of noise. Now, feedback generally does not improve the noise performance of circuits, but there are some cases where it does. So here's an analog to digital converter sensing a sinusoid. We know that the A to D generates a digitized version of the input at the output. And because these two are not exactly the same, it seems that this A to D has corrupted the signal to some extent, right? Because this has these steps in it. So this is what we call noise. You can call it anything you want. It's just some corruption. So I can model this A to D by something as simple as this. I can say that it takes the input, it adds some corruption to it, and generates the output. This is inevitable because we're trying to digitize this signal. We're trying to quantize this signal. All right, so we see that the performance of the A to D is limited by this type of output, by the resolution. So how can we improve this performance? Well, let's take this A to D and place it in a negative feedback loop as shown here. So here's the RA to D, goes right in here, and then we place a negative feedback loop with some amplifier preceding the A to D. So what will happen in this case? Well, we know that the output wants to be a good copy of the input. So even though the A to D is injecting noise here, this negative feedback loop works hard to make sure that the output is a close replica of the input. In other words, we would expect that the output is relatively free from this noise because this negative feedback loop opposes this injection of noise. Again, it all goes back to the principle that this output wants to be a close replica of this input regardless of what's happening here. Okay, so that's great. In practice, though, we replace this amplifier by an integrator, and this is a circuit that we call a delta sigma modulator. Delta sigma modulators act as analog to digital converters, and they are typically used for high resolution applications, typically 14 bits and above. And you can see that it all comes back from the simple principle of negative feedback and the output trying to be a close replica of the input. All right, these were all positive attributes of negative feedback. There are some negative attributes that we do need to worry about. Number one, Negative feedback is not very useful if this gain, A0, which we call the open loop gain, and this gain, y over x, which we call the closed loop gain, are close to each other. So we do need to make sure that the open loop gain is quite higher. In fact, the loop gain, A0 times k, is higher than the closed loop gain. This becomes an issue, for example, at very high frequencies where the gain of this amplifier has dropped so much that it becomes comparable to the gain that we're trying to get from x to y. And number two, negative feedback systems are prone to instability, meaning that they can actually oscillate or they can behave badly, and that requires certain precautions in the design. In other words, what happens is that it is possible, if this amplifier or this loop has a certain amount of delay, so to speak, that this feedback actually becomes positive at some frequency, and when it becomes positive at some frequency, it is possible that the loop will oscillate. So those are important considerations that we need to keep in mind if we are trying to use negative feedback. I hope you have enjoyed the presentation.